Yes, once again, good morning, students. I would invite Deepashri ma'am to start the session.
Hello everyone. Good morning. You sweet. Is my screen visible?
Yes, ma'am.
Yes, ma'am.
Okay. So the last two classes, we discussed about periodic table. We started the periodic table and we know why we read the periodic table, what was the necessity of the periodic table and what was the necessity just to classify the elements, right? Because it was not possible to remember characteristics of each and every component which has been discovered so far, and that is why the periodic table has to be discovered. Otherwise, it was not always possible that yeah, I can remember the characteristics and of each and everything. So many scientists, scholars came forward, gave their theory to discover the periodic table, to discover a basis for the periodic table. And it started with Dauvergne. Dauvergne gave that triad thing. So, but that triad thing was not applicable for all the elements, right? So Dauvernier's idea was rejected. Next came Newland. So he said that if we arrange the elements in order of their increasing atomic weights, every eighth element will have the similar property with the first one, just like a musical note. But again, every element could not satisfy this theory. So his idea was also rejected because at that time inert gases were not discovered, right? So this idea was also rejected. Then came Lothermere. Lothermere just prepared a graph between atomic weight and the atomic volume and tried to tried to classify similar elements with properties that occupy the similar positions on the graph. And he, apart from this, he got some electropositive elements in 1A, 2 has elements like this, and so on. But this idea became a little bit more complex than what people was expecting, and that is why his idea was rejected too. Mendeleev's periodic law, the physical and the chemical properties of the elements are the periodic functions of their atomic weights. So Mendeleev was the first one who gave the old periodic table, and we all know that in the old periodic table, the physical and the chemical properties of the elements are periodic functions of their atomic weights, not the atomic number, it was of the atomic weights. So it means that if we are arranging in order of the increasing or atomic weights, after a regular interval, some similar properties can be seen. And we also know that this Dauvergne said the eighth element will be similar to the first one. Mendeleev said after a regular interval. So that was the difference between Dauvergne and Mendeleev. And then we came to know about periods, we came to know about what I will say, groups and so on. So we, with respect to groups, we know that the long vertical columns that are called groups. And for periods, what are periods? The horizontal rows are called the periods. So in old periodic table and in the new periodic table, number of periods remain constant, but the number of the groups vary. Like the number of the groups in the old table was 9 and in the new table is 18. And the number of periods in both old and the new table are 7. Okay. So the number varies. So we know about lanthanides and actinides. Lanthanides, actinides have 14 elements that were placed separately in the old periodic table, but in the new periodic table, they were classified under F block elements. So we know about this. We also know in the old periodic table, valency of the element was considered with respect to oxygen, Na2O, MgO, Al2O3, SiO2, P2O5, SO3, Cl2O, and so on. From left to right, atomic weight, effective nuclear charge, ionization potential, electronegativity, electron affinity. This will increase. And atomic radius, electropositive character, and metallic character will decrease. So, if we are moving from left to right, certain properties increase and certain properties decrease. We also know about the diagonal relationship where lithium was similar to beryllium and so on. For the groups, we know there are 8 groups and a 0 group. So total there were 9 groups. Groups were divided into 1A, 1B, 2A, 2B. And the elements in group A and the elements in group B, they are quite different. Okay, so in the modern periodic table, this 1A, 1B, there was no existence. There was no such existence. Instead, the 1A elements, 1B elements are being totally separated. Okay, so these were not discovered at that time. So the valency of an element in a group is equal to the group number. So except this, nothing was similar between elements of 1A and 1B. Both have the same group. Both of them have same valency. But except this, 1A, 1B elements were quite different. 1A elements were called the normal elements. 1B elements were called the transition elements. 1B, 2B, 3B, 4B, 5B. All these B things were the transition elements. So there is no resemblance in the elements of subgroup A and subgroup B of same group except the valency. Elements of group which resemble with typical elements are called the normal elements like 1A, 2A, 3A, 4A, 5A, 6A, 7A. These are the normal elements. Those elements of the groups which do not resemble with typical elements are the transition elements like the B things. We know about the hydrogen placed in both the groups. And we know about Mosley. Mosley did a study, and from this study, he concluded this, that the physical and the chemical properties of the elements are the periodic function of atomic number, not atomic weights. So he was the one to propose that let's arrange the elements on the basis of the atomic number, not atomic weights. Okay. So what was the long form of the Bohr's periodic table? So Bohr's periodic table was something based on Mosley's law, that physical and the chemical properties are basis of the atomic numbers. So the long form of the periodic table actually offers different advantages over Mendeleev's classification. This question can be important for your boards, not for your joint. Like there is a demarcation between metals and non-metals. 9 elements of the groups 8 have been placed in separate groups like D6, D7, D8 configuration. 14 lanthanons are not pushed together but are assigned a separate group, and we consider them as the F block element today. So these are some of the advantages of the modern periodic table over the old one. And we know that the lanthanons have the trivalent state. And these 3 electrons go to the inner inert orbitals. That is the reason outer orbitals remains free. None of the electron will be lost or gained. That is the reason lanthanons will be inert. Okay. Since lanthanons will be inert, they can be used as magnets in medical imaging and different types of condition. And transition elements have the bivalence. Why? Because they have the loosely bound 2 electrons in the outermost shell. And this 2 electrons can be lost or can be gained in any condition. So they can be lost actually. So if you consider iron, iron has two loosely bound electrons in its outer state. So iron can actually lose this electron. So that makes it a electropositive. In chemistry, if you are losing any electron, you get a positive charge. Okay, just remember this. The change from a highly electronegative to a high electropositive character through inert gas structure has been explained in the long form of the periodic table. Why? Because Bohr was the first person who gave that atomic model, simplified atomic model, that helped people to realize that the outer shell has free electrons, loose electrons. These electrons can be lost, electrons can be gained in some cases, and thus the physical and the chemical properties of any kind of the element, they I will say that they depends on these electrons, on the valence shell electrons. So Bohr was the first person who gave this idea, who made people realize this concept. Okay, so apart from this hydrogen and this is helium, this is the S block element. We know this is the S block element. This in the middle there is a P block element, and in the extreme right there is a D block element. See, S, P, D, and in the bottom there is the F block element. Okay, so S block elements are what? These are present in the left part, 1A, 2A, and all are metals. And in these elements, last electrons go to the S orbital. And the electronic configuration of the valence shell is NS 1 to 2. And apart from these P block elements mean P block will be present in the extreme right. S block in the extreme left, P block in the extreme right. So these will have the non-metals or kind of metalloids. So, and D block element will also have metals. So up to S block, D block, they will be metal. Everything will be metal, but P block has non-metals. Remember this. And their general electronic configuration is this, except for the helium, where NP6 is not present. D block elements, I just discussed what are the D block elements, and there can be three types of D block elements. 3D, 4D, 5D. We will be learning 3D, 4D, 5D series in the chapter D block elements itself in the future, and the F block elements. So F block elements are mainly the main part that was mainly given a separated space. You can say that, ma'am, in the modern periodic table also they are given separate space. Obviously they will be giving separate spaces. They have characteristics quite different from others. So they act like kind of inert molecules, but they can't be placed under inert molecules. They don't have fulfilled what I will say, fulfilled vacuum valence shell. So they can't be placed with the inert elements. Okay, so that is the reason you just ignore that they can be placed under inert elements. Rather, they are given a separate space, and in this separate space, we generally consider them as what? We generally consider them as the F block elements. Now, till here we have learned what are the inert gases, representative elements, transition elements, inert transition, and the transuranium. So, inert gases we know, representative or normal elements we know, transition elements, modern definition, and transuranium elements. Okay, so this was something we did. So yesterday I told you that anything above atomic number 93 are the actinides, are the transuranium elements. So let's delve deeper into this transuranium element. So the elements of the 7th period after atomic number 93 are synthetic elements and are called the transuranium elements. In 1934, an Italian physicist, Enrico Fermi, had observed that when an element is bombarded with slow neutron, element is transformed into a new element having next higher atomic number. First transuranic element having atomic number 93 was identified by American physicists Edwin Macmillan and Philip H. Abelson. So what was those? Whatever I told, those are the basic thing. And Italian physicist was the first who bombarded an element with slow neutrons, and this gets transformed into a new element. And this new element had a higher atomic number. So this was done with the element with the atomic number 93, and followed by this different other elements came to exist. So uranium 23892 plus 1 neutron, this will give uranium 23892 along with the gamma rays. So the element 93 and 94 were named Neptunium and Plutonium respectively. For Neptune and Pluto, planets were discovered after Uranus. So this was, so transuranium element is just like studying astrophysics. So there can be different elements that can be found on different planets, and afterwards they can be named them. Obviously, this uranium is not found in different planets, no. But just to give you an idea, these elements are mostly used for, I will say, the in the fission. Okay, so uranium fission. So in those works, these elements are being used. So uranium 23892 plus N1 will give uranium 23992 along with gamma rays. Uranium 23992 will produce Neptune 23993 along with the loss of an electron. Neptune will give to plutonium along with the loss of one electron. So these are the different transuranium elements. And 1944, Seaborg and co-workers at the University of California, Berkeley, made new elements 95-96 by bombarding uranium and plutonium with accelerated alpha particles. These elements are named americium after America and curium after Curies. So these are the again different things, like plutonium became americium. So along with the loss of one electron, plutonium along with helium. So this is the radioactive helium. This will give to a new element. It is the curium. Okay, so these are the different transuranium elements and their name. So Seaborg and co-workers bombarded elements 95 and 96 to produce element number 97. See, it is like a chain. From 93, 94 came, 95, 96 were bombarded to produce 97 and so on. Most of the elements were produced like this only. 95, 96 were bombarded to produce 97, 98. And this 97th element is called the Barkiam, and 98 is more known as the Californium. So these are the different things. Along with this, they also produce gamma rays. You will not be encountering with gamma rays in daily life, but working with transuranium elements, you will encounter with gamma rays. Okay. So, okay. Coming back to the periodicity in the properties. So let's discuss this. The term periodicity in property is the classification of element. That means properties of the element reappear at definite interval when the elements are arranged in order of their increasing atomic number. This is the main funda, the main concept, which was proposed by Moseley and Mendeleev. Not Mendeleev, it was actually proposed by Moseley in the modern periodic table. Like, they are asking us, please do arrange the elements in the increasing order of their atomic numbers, not atomic weights. And that is the reason this modern periodic table came into being. Just wait.
Yes, ma'am, we are going to share another screen.
So I guess my screen is visible to everyone. So in the modern
Yes.
periodic table, these intervals are 2, 8, 8, 18, 18, 32. And we have seen this magic number for the old periodic table also. So you can ask me, okay, let's read this slide, then we will explain. That is, the similar properties are observed with elements belonging to the same subgroup, which have been arranged in subgroups after a difference of 2 or 8 or 18 or 32 in the atomic number as well as the valence shell as well as the valence shell electronic configuration recur after regular intervals of the atomic number. This is the cause of the periodicity of the properties. Can anyone volunteer to explain what is this? This is something you have read. This is not something new. So can anyone unmute himself or herself and can please explain what is this? What are they trying to say in this? What is the periodicity? What is the cause of the periodicity? What is the cause of the periodicity? Say anyone? No one?
Ascending,
Anyone? Just say yes, Vignesh.
ascending, ma'am, ascending properties of elements, ma'am.
Yeah, say.
They arrange the elements in the ascending order or descending order, ma'am, in a row.
Yeah, not the descending order, obviously in the ascending order. We will be
Yeah.
arranging only following one trend. But the valence shell is, we all know that the valence shell is the outermost shell, right? Outermost shell of an atom. It is where electrons are present. Electrons present in the valence shell are the valence electrons. Valence electrons are the electrons in the outermost shell of the atom and are responsible for chemical bonding. They can participate. So the number of the valence electron an atom has determined the chemical properties. So atoms with the similar number of the valence electrons, often they have the similar kind of the chemical properties. Till now, is it clear?
Yes, ma'am.
So, what is this 2, 8, 18? So, 2 is the first shell. So, 2, 8, 8, 18, 18, 32. It is a sequence of number that represents the electronic configuration of an atom. So, each number indicates the maximum number of the electron that can be held in a specific energy level or shell around the nucleus. 2 is the first shell, 8 is the second shell, then again 8 is the third shell, 18 is the fourth shell, fifth shell is also 18, and P shell is the sixth shell which has 32 elements. Now this particular sequence, this represents the electronic configuration. Some elements, you can see that for some elements, they have only 2 electrons and they are happy. Helium, right? So helium has 2 electrons and it is happy. It has the stability. Some has 8 electrons in their outermost shell and they are happy because it is stable. 18 electrons, it is also a kind of stability. 32, it is also kind of stability. Why we know this? Because hydrogen, helium, lithium. Lithium will have one more extra electron. So lithium will try to add, okay, see this chart. See, helium has 2 electrons in the outermost shell, okay? And lithium will be 3, means it has one more electron. So lithium will try to act like helium. Obviously, you can say, why will not lithium try to act like neon? Because lithium is closest to helium, right? Suppose you have a sibling who is extraordinarily talented. Okay, so will you, and there is um, another famous man in the country who is also talented like your sister. Both are talented, but who will inspire you to more? To be talented or to be successful like him or her? Obviously, your sibling. Because you are seeing your sibling from a closer look. So lithium is seeing helium from a closer look. So lithium is closer to helium than lithium is closer to neon. So obviously lithium will lose one electron to be 2. So we write Li plus. Similarly for sodium, sodium will not try to act like helium. Sodium will try to act like neon. Right. So no, sodium has 11 electrons, neon has 10 electrons. Sodium will try to lose 1 electron. See, it does not matter whom they try to be. Lithium tries to be helium, sodium tries to be neon. The fact is that they both try to lose 1 electron. And that is why they are under group 1. Okay. Did you get this concept that why lithium, sodium, potassium, rubidium, cesium, francium all are on the same group? Is this part clear or should I explain again?
Ma'am, can you explain once again?
Okay, I will explain again. See, hydrogen has atomic number 1. Helium 2, lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, sodium 11, magnesium 12. Then again, aluminium 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17, argon 18. We have arranged this on the basis of increasing atomic number. Okay. Now, so lithium, consider lithium. So see, this part, helium, neon, argon, krypton, xenon, random, and this is opposition, I guess. So these elements, they have fulfilled orbital, fulfilled valence shell, like 2, 8, 8, 18, 18, 32. This valence shell has 2 electrons. This valence shell has 8. This valence shell has 8. This valence shell has 18. This valence shell has 18. This valence shell has 32. Till now, is it clear?
Yes, ma'am.
Okay. So, we know these elements are what? Inert.
Yes, ma'am.
Up to this, helium to radon. These are what? Inert. Inert means they will neither lose electron nor gain electrons, right? Okay.
Yes, ma'am.
When will this condition will be arised? If their valence electron is fulfilled, right? Then they will have the stability and they will neither try to lose electrons nor they try to gain electron, right? Okay. So having 2 electron, 8 electron, 8 electron, 18 electron, 18 electron, 32 electron, respectively, in their valence shell is equivalent to giving them stability. Okay, means helium has 2 electrons in its valence shell, it is inert. Neon has 18 electron in its valence shell, it is inert. Argon has 18 electron in its valence shell, it is inert. Sorry, 8 electrons in its valence shell, it is inert. Krypton has 18 electron in its valence shell, it is inert. Xenon has 18 electron in its valence shell, it is inert. Randon has 32 elements in the valence shell. It is inert. Okay. So all other elements in the periodic table except this, all the other elements from here will try to be like this. These are the people with government jobs. Okay. Helium, neon, argon, krypton, xenon, radon. These are the people who have cracked Neet. These are the people who have cracked IIT. And all others, they want to be like this. Okay. Now, suppose you have a sister who cracked Neet in first attempt, and not only cracked Neet, but scored very good. Okay. And there are hella lots of people on planet Earth who have cracked Neet so far till date, right or wrong? Now, who will inspire you to crack Neet in first attempt with an exceptional degree, with an exceptional good rank? Obviously, your sister. Suppose you already know a lot of people has cracked Neet, scored the full marks, and yet they are quite distant from you. You don't know the toppers. But if your sister has cracked the Neet, has become a topper of Neet, your sister will be making you more inspired. Right? You will be more inspired by your sister. Right or wrong? Similarly, lithium. So lithium will try to be like neon. See, these elements can be like anything from them. Okay. But the rule is whoever is the closest, they will try to act like them. Lithium will try to act like helium. So helium has 2 electrons, lithium has 3. So lithium will think, let me lose 1 more electron. Then I will become Li1 plus. And I will have the same electronic configuration as helium. So I will be stable. It's just like you are seeing a topper and you are following the time schedule of a topper to become a topper. So lithium has lost 1 electron. So the electronic configuration of lithium becomes similar with helium. Okay, is this part clear?
Yes, ma'am.
Okay, so now for sodium, see, sodium will try to act like helium. See, from helium, this entire line has passed, then came sodium. So, till this, another topper came, which is neon, and then sodium. So, sodium will be more influenced by neon and not helium. Okay, so neon has 10 electrons, its outer shell has 8 electrons, and sodium has 11 electrons. Okay, so sodium will think, let me lose 1 more electron. Then I will be Na plus 1. Then I will have the same electronic configuration as neon. I will gain stability. If sodium wants to become like helium, then it will have to lose a lot more electrons. Suppose there are 2 toppers. One topper has given you mnemonics. Mnemonics means short trick to memorize an answer. Another topper has asked you to study 24 hours a day. So whose advice are you going to follow? Obviously, someone who has given you tips and tricks. So sodium will be more influenced by this neon. That okay, neon is closer to me. I will be influenced by neon. To be influenced by helium, I will have to follow a lot more rules. So why will I do that? I will be doing this bare minimum to get the maximum output. Like we all do. We will be starting the least and we'll get the maximum result. We all think like this, right? So that is the reason sodium will try to look like neon. Now see, lithium tries to look like helium and loses one electron. Sodium tries to look like neon and loses one electron. Potassium tries to look like argon and loses one electron. So they try to look like different elements, but they always lose one electron. So that is the reason they are in group 1. Okay. Is this part now clear to everyone?
Yes, ma'am.
Okay. So this is the basic concept. So that is what has been said. So this is what has been said here. This is the cause for the periodicity. Like say lithium 3, it has the electronic configuration like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6. I guess 1s, 2s, 3s, you can know how to write because you have already completed the atomic radii chapter, not the atomic, the first chapter. I forgot the name of that chapter. I guess you have all learned that chapter, and that is why you came here. So you all know how to write the electronic configuration. Okay. Thus, the cause of the periodicity of the property is the repetition of similar electronic configuration of their atoms in the outermost shell. See, lithium will try to lose one electron, just now I told, and see its valence shell has one electron. All their valence shell has one electron, and up to this, they will gain stability. Okay. So they will always, so remember, if anyone has 2 electrons in the, not anyone, helium has 2 electrons in the outermost shell. That is why it is becoming stable. So always remember that magic number 2, 8, 8, 18, 18, 32. So you can follow the chart, and for that element, you will know that for this element, to be gaining a stability, 32 valence electrons are needed. And for francium, do I have 32 electrons in the valence shell? Obviously, yes. So I have one more extra electron. So they will try to lose this one more extra electron. This is the basic concept. Okay. Elements are lazy. They will do the minimum work to get the maximum output. And never in life you will see any atom or any kind of cell to be working without any reason. Everything has a reason, mostly. This is the basic concept. Okay. Atomic radii. What is the atomic radii? Defined as the distance between the nucleus and the outermost shell. That is the valence shell. So how do you calculate radius? Is the same manner how do you calculate the radii of an atom. Right from the center of the nucleus, from there you will start drawing a line up to where? Up to the valence shell or the outermost shell where the electrons are present. So that is the atomic radii. 3 types of radii are covalent, crystal, van der Waals. So what is the covalent radii? Covalent radii is defined as half of distance between 2 nuclei of 2 like atoms bonded together by single covalent bond. 2 similar types of atoms like carbon, suppose they are bonded by single bond. Okay. So covalent radii is half the distance. Okay. Half the distance between them. So this is the general formula. So considering a homonuclear diatomic molecule, suppose A and A. Okay. They have a single covalent bond in between. So we can assume that the electron clouds of each of the atom touches each other. And thus, the bond length is like this. Okay. 2 Ra. Obviously, radius of one Two atoms, I said, radius of one atom plus the radius of another atom. Okay, so this is the covalent radii. So if we want to consider radius of one, so it is just the half. So that's what I am trying to say. Is this part clear? Is this part clear?
Yes, ma'am.
Okay. So basically in a covalent radii, I will say it is the measure of the size of an atom when it is bonded to another atom by a covalent bond. And it is half the distance between the nuclei of two identical atoms. Okay, so this atomic radii will generally decrease along a period, and along a group it will increase. Okay. So in a heteronuclear diatomic molecules like DAB molecule, if both atoms are linked by a single covalent bond and have nearly same electronegativity, bond length is equal to the sum of those covalent radii. Just simple. Here what was happening? Here two same atoms were present. Two radius we are calculating. See, here RA and RB we are writing. Here RA plus RA we are writing, which is equal to 2RA. Okay. And if we consider RA, that will be half. That is different thing. But this will be DA. Okay, so and what is this? DAB, it is just the summation of the two radii. If the covalent bond is formed between two elements of different electronegativity, then this can be the relationship. So we have formulas to calculate the atomic radii in between two atoms which are identical, AA. Then we have a formula to calculate the atomic radii between two atoms which has same electronegativity, almost. Okay, the carbon and something from the carbon family. Both has almost same electronegativity. So there we will be using that formula. But here, they have different electronegativities. Like if suppose carbon and hydrogen, and we want to find the atomic radii. So we will be using this formula. This relationship was given by Stevenson in 1941. Crystal radii. It is defined as 1/2 of the distance between nuclei of two adjacent metal atoms in the metallic closed packed crystal in which metal exhibits a coordination number of 12. So it's just simple. Two metallic ions are present. Their distance, just half it, that is the crystal radii. But this metal atom should have a coordination number of 12. Van der Waals radii, half of the distance between the nuclei of two non-bounded neighboring atoms of two adjacent molecules. So this is the basic relationship, and this relationship comes in your exam. R van der Waals, R crystal, R covalent. Okay. Atomic radii in the in the nth orbit is given by Rn n square a naught by z star. N is the principal quantum number, that is the number of shell basically. A naught is the Bohr's radius. Z prime is the effective nuclear charge. So Z, the value of Z will be given to you. Okay, so N is the principal quantum number. So for in the first chapter, I guess you have learned about principal quantum number, azimuthal quantum number, these quantum numbers, I guess. A naught is the Bohr's radius of the hydrogen atom. Okay. Next comes the screening effect or the shielding effect or the effective nuclear charge. What is this? In a multi-electron atom, the electrons of the valence shell are attracted towards the nucleus and repelled by the electrons present in the inner shell. So in a multi-electron atom, electrons of the valence shell, they are attracted towards the nucleus, but they will be repelled by the electrons present towards the inner shell. Obviously, the laser point is not working. Okay. So just imagine, follow my cursor. This is an atom. Here is the nucleus in between, and there are different other shells. Obviously, a single atom will not have a single shell, right? There will be multiple shells. So the electron present in the outermost shell, nucleus has what? Neutrons, protons. Proton will try to attract the electron towards itself. But the electrons present within the other shells, they will try to repel this. Okay, they will try to repel these electrons. So this is the screening effect or the shielding effect or the effective nuclear charge. Is this concept clear? Is this concept clear?
Yes, ma'am.
Okay. So on account of this, the combined effect of this attractive and repulsive force acting on the valence electron is that the valence electron experience less attraction from the nucleus. The decrease in force of attraction exerted by the nucleus on the valence electrons due to the presence of electrons in the inner shell is called the screening effect or is referred to as the shielding effect. So someone from the inner core, someone sitting right inside at the center of the house, they are inviting you to come, but the guards are not allowing you to come. Okay, suppose there is a house and in the core of the house, someone, your friend has invited you to come but during the exam, but there are other guards surrounding his house, like his mom, dad, all are present surrounding his house. They are saying, you know, this is an exam time, you can't come. So will you be able to reach, will you be able to respond to the force of attraction present right at the center? No, your force of attraction will decrease. You will think, okay, his mom and dad is not quite happy to see me during an exam. So obviously, I will not feel that part of the attraction. Whereas on the other hand, if these guards were not present, if his mom and dad was out of town, you could have easily gone inside his house, right? So this is the shielding effect or the screening effect. So this decrease in the force of attraction exerted by the nucleus on the valence electrons due to the presence of electrons in the inner shell is called the screening effect or the shielding effect. So obviously, the nucleus will also see, okay, my guards are present, so I can't force this force of attraction on the electron. Okay, so the nucleus will also reduce its force of attraction. So that is the shielding effect. Is this part clear? What is shielding effect? So let's do with this effective atomic number, then we can end the class. So what is this? Due to screening effect, valence electron experience less attraction towards nucleus. Just now we did. This brings decrease in the nuclear charge actually present in the nucleus. So the nucleus became sad and the nuclear charge decreases. The reduced nuclear charge is referred to as the effective nuclear charge and is represented by Z star. Okay, so what is happening? Your friend is sitting at the center of the house. His mom and dad is guarding him. Is okay during an exam time. Now his friend is, now your friend has attracted you. Come to my house. I'm too bored studying. I don't want to study. You are coming to his house. Now the parents will throw you away. This is an exam time. No, don't come to our house. So by this repeated repulsion, your friend will see, okay, this is creating a problem. So I will now reduce my force of attraction towards you. So you are not coming. Obviously, nucleus has seen this. So nucleus has now become sad. And as a result, your friend became sad. So your friend becomes sad, and as a result of this, he is suffering from depression. So that is what happening here. This brings decrease in the nuclear charge, which is Z present on the nucleus, and the decreased nuclear charge. This whole condition is referred to as the Z star. So Z star is the decrease in the nuclear charge due to screening effect. Okay, and this Z is the original nuclear star, original nuclear charge, and Z star is the decreased nuclear charge. Okay, so it is related to actual nuclear charge Z by the following number: Z minus S is the screening constant. So S is determined by the Slatter's rule, and we will be learning about this in next class, that why we are learning about the effective atomic number. So is the whole concept for effective atomic number, Z star, Z, screening effect, is this part clear to everyone in this class? Did you understand each and everything I have told since last 1 hour? Is this part clear?
Yes, ma'am.
Okay. So this is something. So we will be continuing in the next class why we are learning this screening effect and so on. So wait. Yes, ma'am. That was all from my end for today. Ma'am, students just join the next class. Okay. Notes will be sent to you by sir. I don't have these notes. Sir will be sending you these notes. Students join the next class, okay?
Yes, students, you can join the next class. Thank you. Thank you, madam.